Hello, Math 113. Let's talk about complex numbers and DeMoivre's theorem. So first, let's just spend a few minutes reminding ourselves of what complex numbers actually are. It'll take a while to get to DeMoivre's theorem, which, by the way, I did look up the official pronunciation. I've always heard as a student that was DeMoivre's theorem, and I may even revert back to that really simple way of saying it, but I did look up the pronunciation, and it's DeMoivre, M-O-I, DeMoivre's theorem. And the French person that described that to me says that Americans can't really say it properly, so I just need to say DeMoivre's theorem, but know that that's not correct pronunciation. But it'll take a few minutes to get there. Let's just talk about complex numbers. When you look at a complex number, when you see a complex number, I know you know it. They look like, bottom right corner here, say 3 minus 2i. You probably remember that from a pre-calculus algebra course, which could have been just a few weeks ago, or it could have been several years ago. Now, how do they come up? The majority of time that you see complex numbers is when you're trying to solve equations. In particular, quadratic equations can have imaginary or complex solutions. They come up in pairs like 3 minus 2i and 3 plus 2i. So those are considered complex numbers. If the 2 happens to be a 0, so 3 plus, let's say, 0i, that's actually considered a real number because the imaginary part is 0. Okay, so notice that's listed in my diagram here, right here, a plus 0i. All real numbers are of that form. In the imaginary numbers listing, it's a plus bi, and you can have a purely imaginary number like, for instance, 2i. Okay, so it'd be like 0 plus 2i. If you only have 2i there, then that's called a pure imaginary number. But all of these are called complex numbers. All the real numbers you know are complex numbers. And then you have these of the form a plus bi. Now, I kind of like this diagram, although it's not absolutely perfect. I think it's probably impossible to draw an absolutely perfect diagram to represent all of the numbers that we know in mathematics. But let's start in the center. You know, natural numbers. You know those guys right there. That is your counting numbers. 1, 2, 3, 4, 5. Of course, that goes on forever. And then the whole numbers is that same group of numbers. We just add 0 in there. So it's 0, 1, 2, 3, 4, 5. What are integers? Well, it's these numbers, both positive and negative. So when you're talking about the integer list, you say, you know, -3, -2, -1, 0, 1. That continues forever, left and right, to plus infinity and minus infinity. What are rational numbers? They're fractions, like 1/2 or 2/3. And every natural number, every whole number, every integer can be written as a fraction. So for instance, 5 can be written as 5/1, right? And then outside the rational numbers are irrational numbers. Now those are numbers that cannot be written as a fraction per definition. Like, say, square root 2 is an irrational number, or 1 plus the square root of 5 is an irrational number, or pi, the most famous irrational number of all, right? Those are all irrational. So real numbers are either rational or irrational. And that's the part about this diagram that I'm not a fan of, because it makes you wonder what's happening out here in the blue area. Absolutely nothing. So you are either irrational or rational if you are a real number. Nothing exists in this blue area. Okay? Now, again, the imaginary numbers, you know those as, say, 3 plus 0i or 3 minus 2i. Now, what's really neat and weird about imaginary numbers is you can't compare them. For instance, is 1 plus 5i, is that greater than or less than 2 minus 3i? You know what? We can't tell. It doesn't have the transitive property. You can't say 1 imaginary number is larger than another imaginary number. That is only a property of real numbers. So these imaginary guys have some unusual properties, let's just say that. Okay, not like your real numbers. So you know how to work with these, but just as a reminder, I want to do a few problems. So you remember complex numbers, a plus bi, also called imaginary numbers as long as b is not equal to 0. You can add them, subtract them, multiply them, you can even divide them. Now in this section, you may have to do a little bit of this operation. That's not really where the focus lies, but I need you to understand complex numbers, at least how to work with them before I jump in to complex numbers in DeMoivre's theorem. Okay, and by the way, this is a trigonometry class, I swear, but it's going to take a few minutes to even see how this has anything to do with trigonometry, and right now it doesn't. We're just dealing with numerical things. Now when you add complex numbers, remember you add the real part, so 3 plus 2 is 5, and you add the imaginary part, 4i plus a negative 5i is a negative 1i. Now, because that's a 1 times I, you can write that as 5 minus I. And you always write imaginary numbers in standard form the same way, with the real part first and the imaginary part second. How do you subtract them? Same method. You subtract the real parts and you subtract the imaginary parts, but be careful because this subtraction does apply to both of these terms, so to speak, inside the parentheses. I would distribute first. So you could write this as 3 plus 4i minus 2 plus 5i, and then just add like terms. So 3 added to a negative 2 is going to be 1. 4i added to 5i is plus 9i. Okay, now when you multiply, it's a little bit more work. So you do use the FOIL method, first, outer, inner, last. So 3 times 2 is equal to 6. 3 times negative 5i is negative 15i. 4i times 2 is plus 8i. And then 4i times negative 5i is negative 20i squared. Now that is not standard form for a complex number, and we know the answer to this is a complex number. So I'm going to go ahead and add my I values together. It's like terms. 6, negative 15 plus 8 is negative 7i, and then negative 20i squared. Now this is important. You recall what I squared is. I hope you do. Remember, it's negative 1, so this is minus 20 times negative 1. So this is really 6 minus 7i plus 20. Most of us, when we see an I squared, we really just know that we're going to change this operation right here. So minus turns into plus, and you drop the I squared. Finally, the real part, 6 plus 20 is 26 minus 7i. Is the final answer, again, in that standard form for a complex number. Now, the worst of this, and it's still not bad, is division of complex numbers. How do you do that? You multiply by what's called the complex conjugate of the denominator. So I'm not changing the sign of the denominator. I'm doing the opposite of operation. So 2 minus 5i, the complex conjugate of that is 2 plus 5i. If I multiply that in the denominator, of course I have to multiply that in the numerator also. So really I'm just multiplying by the fraction 1. It's a crazy looking fraction 1, but it is equal to 1. So I'm not changing the value of my original number over here. Now this means I have to FOIL the top and the bottom. So 3 times 2 is 6. 3 times 5i is 15i. Easy to make simple mistakes here. 4i times 2 is plus 8i. And then 4i times 5i is going to be 20i squared. Okay? Be careful with your I squareds. In the denominator, I'm going to FOIL again. 2 times 2 is 4. 2 times 5i is plus 10i. Negative 5i times 2 is minus 10i. And then negative 5i times plus 5i is negative 25i squared. Now, did I leave myself a room to get this finished? Yeah, maybe if I cheat a little bit and do some work in my head. So for instance, 20i squared turns into negative 20, correct? So 6 minus 20 is going to be negative 14 in the numerator. 15i plus 8i is 23i. Again, this is supposed to be review, but I would make sure you're comfortable with all this. 10i minus 10i cancels. Negative 25i squared. Remember, I squared is negative 1, so that's plus 25. Plus 4 is 29. Now, to be truly in standard form of a complex number, I've run out of space, so I'm scooting up here to the top. I'd write that as negative 14/29 plus 23/29 I. And that is that. So this is review, but I just wanted to review operations with complex numbers to help you think about what we have to do in this section. Now here's something maybe you've never seen before. We can graph complex numbers, again in standard form, that's a plus bi, on something called the complex plane. Okay, what does the complex plane look like? It looks just like the XY axis or rectangular coordinate system, or, you know, Cartesian coordinate system, just regular old XY axis, but it's a little bit different. The horizontal axis, we normally call that X, right? That is your real values, okay? Whereas this is your imaginary values. So it's like the y-axis is the imaginary and the x-axis is real values. Okay, this is also called the Argand plane. You may see the term Argand diagram, and that's when you graph complex numbers in an XY axis. It's also called the Gauss plane. Okay, so if you hear any of those terms, it's really referring to the complex plane, where here I have it typed for you. The real axis is horizontal. That compares to the x-axis, but it's no longer the x-axis. And the vertical axis, used to be the y-axis, is the imaginary axis. So I want to take a couple of minutes and just graph a few complex numbers in the complex plane. So if we graph 3 plus 5i, we go over to 3 along the real axis. You see 3 right down here, okay? And then you go up to 5i and you plot that point just like you would plot a ordered pair. So this represents the point 3 plus 5i. And actually parentheses are really not a requirement, so I'm going to get rid of them. There we go. Okay, so there's 3 plus 5i. All right, you take a minute and graph those other 3. Did you get it done? So negative 2, go to negative 2 on the real axis, and then down 1 to negative I. So this is negative 2 minus I. All right, let me change colors on you. How about, let's go green for 3i. So when there is no real part, remember that's 0. So this is the same as 0 plus 3i. So 0, real part along the what used to be x-axis, or the real axis down here. You don't go left or right, you just go up to 3i. So this represents 3i. And then finally, negative 4 is like saying negative 4, okay, I'm sorry, negative 4 plus 0i. So you go over to negative 4, but since 0 is I, you are right there at negative 4. Super easy, right? Super easy. Now, why would you ever want to do a thing? What would motivate you to graph complex numbers on what looks to be like an XY axis? Well, we're not going to get deep into that, but we do have one use of thinking about that anyway. Okay, and I'm going to show you what that is, but not quite yet. It's coming, I promise, fast. What about the absolute value of a complex number? Which brings me to, what's absolute value anyway? Okay, what does absolute value mean? Well, by definition, if you want to pause me and go look that up on your own, awesome. I applaud you. If you want to just wait for me to tell you, I will. The absolute value of a number is a number's distance from 0. Now, I know a lot of you are thinking, it's just positive. You make it positive. Well, you do. But the absolute value of a number is a number's distance from 0. Okay, so let me write that down. That's not something you have to memorize. It really is something you should know. But I'm saying this to help you think about the absolute value of a complex number. Remember, we talked about complex numbers earlier as in the case that they're weird. You can't tell if one complex number is larger than another complex number because they don't have the transitive property where you can tell one is larger than another. You could just say they're either equal or they're not equal, and that's about all we got. But we can tell how far a number is, a complex number, from 0. How do you say? Well, here we go. Back to our complex plane. Remember, we could also call that an Argand plane or a Gauss plane or an Argand diagram. All that doesn't really matter that much right now. I'm just talking. But 2 plus 3i. Let's plot that in the complex plane. So 2 is the real part. The 3i is the imaginary part. So we go real part 2, 3i. So that point, uh-oh, my pen's not working. Stand by. Okay, here we go. 2 plus 3i. Here we are, right here. There is 2 plus 3i diagrammed or plotted in the complex plane. Well, what's with the vertical bars? Remember, that means absolute value. Okay, so anytime you see vertical bars around the number, that very, very likely means the absolute value. It's a number's distance from 0. Okay, can we tell, let me graph this line in blue, how far this is from 0? Well, if we could tell how long that, there's 0 right there, right in the middle. If we could tell how long that line is, we could tell how far 2 plus 3i is from 0, at least in the complex plane. Well, how do we tell how long that line is? You might be thinking, correctly, use the distance formula, right? Anytime you have to tell the distance of a line in the xy axis, you could use the distance formula. But now this is an xy axis, it's the complex plane. Well, let's think about it this way. It's still going to be the same idea. We do know how far this is, right? That's too long. We do know how far this is. That's 3 long. If that's 3 and that's 2, right? From 0 to 2 is 2. From 0 up to 3 is 3. Can we find out how long this is? You better believe it. Pythagorean theorem, right? So I could take 2 squared plus 3 squared is equal to, I'm just going to call that over there c squared. As a matter of fact, in a few minutes, you're going to see this down here labeled A and this B, and there you go. You could call that C, although we don't in a minute. So I got 2 squared is 4, plus 3 squared is 9, equals C squared. That's 13 equals C squared. How long does that mean C is? Yep, the square root of 13. Okay, so 2 plus 3i's distance from 0 is the square root of 13. Now, instead of doing the Pythagorean theorem every single time, let's just do a formula, right? So the absolute value of z, remember absolute value, vertical bars, is the same thing as saying the absolute value of a plus bi. By the way, z represents a complex number. So just go ahead and put that in your brain. When you see z, that typically represents a random complex number or a particular complex number. And it's of the form a plus bi. And to find its absolute value, you can use the Pythagorean theorem just like we did, or you can take the square root of a squared plus b squared. Okay? Now, if I draw that out for you, you can see this happening. Now, let's just do this. Find the absolute value of the complex number -3 minus 4i. So, what do? If I use the formula, that would be the absolute value of -3 minus 4i is equal to the square root of -3 squared plus -4 squared. What about the I? Not part of the formula, right? You're not squaring the I, so don't do that. You're just squaring the real part and the real part of the imaginary part. So the A and the B, you go ahead, if they're negative, you square them. If you leave off the negative, you would actually still get it right? Because you're squaring it, and then don't forget to take the square root. So this is going to be 9 plus 16, which is the square root of 25, which of course is 5. So the absolute value of -3 minus 4i is 5. Why? Well, where's negative 3 minus 4i? So we go negative 3 and then negative 4i right here. That distance from 0 right there is 5 units long. And it really just comes from the Pythagorean theorem. Now you might have noticed I am 20 minutes into this lecture, and this seems to have absolutely nothing to do with trigonometry. Here comes the trigonometry. Okay, so I've got a diagram for you. Remember over here, this is your point, which really represents a complex number, a plus bi. Remember, a is the real part. So a right here, the real part, is represented at the bottom. That's that distance at the bottom. This is a. Okay. On the other hand, b, let's go pink, is your imaginary part. All right. That's right here. And that represents this distance right here. Okay. Now, where's this cosine of theta and sine of theta business coming in? What in the world have we done here? All right, so let's think about it this way. Remember way back, at the beginning of your tree class, which might be a few weeks ago, it might be a few months ago, but we had definitions for all 6 of the trigonometric functions for any angle. Do you remember that? One of them was sine of theta is equal to y over r. Another one was cosine of theta is equal to x over r. Those are official definitions, okay? Now, if I solve this for y, I would have to multiply both sides by r, and I get y is equal to r sine of theta. You probably recognize that also from polar coordinates, which you likely just completed. If you're changing from rectangular equations to polar equations, you would need that same formula. Right here, if I multiply both sides by r and I isolate the x, I'm going to get x is r cosine of theta. I find that a lot of people don't follow me on that. So here's what I'm doing. I'm multiplying by r, this cancels with that r, and then I have it right there. Y is equal to r sine of theta. Multiply by r, the r's cancel, x is r cosine of theta. Now, if we translate that to our picture over here, instead of calling this along here x, we just called it a, right? And that matches what we have graphed. This a, the real number part, is always along this way. The imaginary part is always up and down this way. So now we can change a complex number in that a plus bi form, which I called earlier a standard form. Now they're going to call this a rectangular form. We can use these substitutions that b is r sine of theta and a is r cosine of theta and change it to something called polar form. Okay, so follow me across the bottom here. Same diagram, right? If you have z, remember we're going to use z to represent a complex number. It's of the form a plus bi, just regular old complex number form. We called it standard form earlier. Now we're going to call it rectangular form. If I substitute, remember I highlighted this in that aqua color. If I substitute a with what a is, r cosine of theta, okay, and I substitute b right here with what b is, r sine of theta, and remember the I is just part of the representation of the number, I could factor out my common r's. So r here, we're going to put it out front. And now the polar form of a complex number is r times parentheses cosine of theta plus I sine of theta. And the official definition is right here in yellow. A few things I want to point out here, and then I'm going to stop the video and make a part 2. Okay? Very important. So the polar form of a complex number is z is equal to r cosine of theta plus I sine of theta. Okay, now that is a memorizer, but remember that comes from plotting this in the complex plane and using our definitions of sine and cosine for any angle. All right, now let's keep going. The r value, okay, that is your absolute value of your complex number. So notice here it is. In your definition, your r, right here, is the square root of a squared plus b squared. That is the absolute value of the complex number, and it is called the modulus. Notice it says if you have more than one, it's the moduli, but it's the modulus of your complex number. You also have a theta value that you need to find, and it is called the argument. How do you find it? You're going to recognize this from polar graphing also. Tangent of theta is equal to b over a. Remember? So the definition for tangent is sine of theta over cosine of theta, or your y value over your x value. Well, the y value is b, and our x value is a. See, those are all definitions that you know, but suddenly applied to complex numbers. And the only reason this happened is we plotted a complex number in what we call the complex plane. Okay? No, it's a lot to take in, right? So no, I'm not going to pause it just yet. Let's do a problem where we plot a number and then we change it to polar form. And I might have a couple of those before we pause it and move to part 2. All right, so we're supposed to plot 1 plus I square root 3. Now, I don't know if you've noticed this. Sometimes the I goes in the back, and then sometimes it goes in the front of the number. Why? Because, now y'all, the whole time I've been teaching, this hasn't been the case. Used to, when I first started teaching, I saw this number written like this. Okay, with the I always in the back. Why in the world would we change it to this? Why would we do something like that? Because let me tell you what, students get lazy, and we all do it. Instructors get lazy too. And sometimes the square root goes too far over the I, and that's not the same thing as this. So to avoid something like that happening, if we have a radical in our imaginary part, we put the I value first. Okay? We also put it before trig function. So sometimes you'll see the I in the front, sometimes you'll see the I in the back, and it's really a matter of opinion, but there's more accepted ways of writing it than other ways. Okay, now what are we supposed to be doing? Not talking about that. We're supposed to be graphing, right? 1 plus I squared root of 3. How am I going to graph that? Remember, 1 is the real part. So I know I go over to 1. Don't make a mark yet. I've got to go up square root of 3. Well, I can't. How am I supposed to graph square root of 3? Now, that's what your calculator's for, right? Type in square root of 3 in a calculator. If you've been doing trig like you're supposed to, you probably have seen that so many times you know exactly what it is. But if not, it's 1.7325. So this is like plotting 1 plus 1.73i rounded. So plot that the best you can. Here's 1, and then 1.73, almost 2. I'm going to put it right there. And this is 1 plus I square root of 3. Okay? Easy enough. Now, we need to change this to polar form. So there's 2 things you've got to do before you can even begin to write this in polar form. You have to find your modulus, and we call that R is equal to, remember, you're just finding the absolute value of your complex number. So that's going to be your real part squared plus your imaginary part without the I. Don't ever put an I in there, squared. Just square each one and add. That's going to give you the square root of 1 plus 3, which is the square root of 4, which is 2. So your R value is equal to 2. You also have to find your argument. Remember, tangent of theta is equal to your B over A. So my B value is square root of 3. My A value is 1. So tell me what angle gives me square root of 3 when I take the tangent of it. So you have to think backwards. Remember, you have to know this unit circle. Now the big question is, should we do this in degrees? Or should we do this in radians? Well, you're going to find out the homework tends more to degrees than they do radians, but they do ask for both. The directions that I have here don't specify, and they really should, because you couldn't do this otherwise. So we're going to do both because I didn't specify in polar form. Do I want polar form in degrees, or do I want polar form in radians? They are both appropriate. So first, let's do this thing in radians. Why? Because when you take calculus, you need to be thinking in radians more than you do in degrees. So here we go. Tangent of theta is equal to square root of 3. You need to know by now that this is square root of 3 over 2 over 1/2. That is your y value, that is your x value, or your b and your a value. What angle does that happen? Remember, this is the unit circle that lives in my head. And that happens right here at pi over 3. Now, you got to know what quadrant you're in, okay, because it actually happens in two places. It happens at pi over 3, okay. Where else is tangent positive? Well, right down here in quadrant 3, and that's at 4 pi over 3. Now, remember, in polar form, just like polar form, there's not two different correct answers. It's either this angle or this angle down here. How do I know it's this one? Because look, I'm in quadrant 1 right here, so it has to be the quadrant 1 situation. So our theta is equal to pi over 3. Well, what's that in degrees? Y'all know, that's 60 degrees, right? So I have two ways I can write this. One correct answer in radian form would be that z is equal to, remember, the r goes out front, so that's going to be 2 in parentheses. It's going to be cosine of pi over 3 plus, don't forget your I, sine of pi over 3. That is an appropriate answer. Since it didn't say it had to be in radians or degrees, another appropriate answer would be 2 cosine of 60 degrees plus I sine of 60 degrees, okay? Again, both of these are correct. In the homework, read carefully because it will say either in degrees or radians. Okay, I'm going to pause the video. I'm going to come back for part 2, and likely I'm going to do another problem like this to get you started with the next part of what we need to do in this section about DeMoivre's theorem. All right, y'all have a good one.